Hello, I am Anand Gupta. I teach physics at IIT Gandhinagar and work in gravitational waves. I've been lucky to live in a time when physics has changed before our very eyes, from the discovery of the Higgs boson to detecting gravitational waves from merging black holes to graphene and its remarkable properties. So these breakthroughs have not only just expanded our understanding of the universe, but they've changed how we think about matter, energy, and even life. For years, I've wanted to sit down with my colleagues to understand what drives their curiosity and what it feels like to work in these areas. That thought came alive again during our conference celebrating 10 years since the first gravitational wave detection. It felt like the right moment to begin this series in conversation with AnandO. In each episode, we'll meet researchers shaping modern physics, talk about how their work is changing the landscape, and where it might take us next. I hope you enjoy the journey as much as I do. It has already been 10 years since the first gravitational wave was detected, and GW150914 was that extraordinary moment when the universe spoke to us through ripples in space and time. So we are here at IIT Gandhinagar, which is hosting a special conference to celebrate a decade of that discovery, bringing together many of the scientists who helped make it possible. So with me today is Professor K G Arun from Chennai Mathematical Institute. And Arun is one of the leading figures in gravitational wave physics and a torchbearer of Professor Bala Iyer's pioneering group at Raman Research Institute in Bangalore. So Arun has been central to the story of accurate waveform modeling, testing general relativity, and now also in shaping India's own chapter in this field through the LIGO-India scientific collaboration. So we'll talk about that journey from having equations on paper to a detector that is rising on Indian soil. And we'll also crystal gaze a little bit to understand where the next decade of gravitational wave astronomy might take us. So welcome, Arun.
Thank you so much, Anand.
It's a pleasure to have you here on campus. So it has been 10 years, right, since the discovery of GW150914. So when you look back, what's your most vivid memory from that time?
Yeah, so as you know that once the first detection happened, its announcement was a big news, but for those who are inside the collaboration, it was a very slow process to digest it. So the kind of high moment was when we really know that it was not a blind injection. Right? So blind injection, for those who do not know, are like hardware injections into the data for checking whether analysis pipelines are doing well, which are not disclosed to everybody else. Very few people know it. So they do it randomly. And when we were analyzing, we were thought this may be one of the blind injections and not a true signal. But the moment the kind of lead people in the collaboration told us that it is not a blind injection, we were all like, this is an incredible kind of thing. So that's probably the highest. Then onwards, I think we were all kind of woken up. And
So let me also ask you, how did you first get involved with the gravitational wave community?
Yeah, so I did my PhD with Prof Bala Iyer, and there I was doing post-Newtonian, theoretical calculations, computing gravitational waveform, which are used in the analysis because of the match filtering techniques. But that was, of course, a small group at that point. But my first involvement with a major collaboration was when I went for my first postdoc to Virgo. It was in Linear Accelerator Laboratory in Orsay, and I was sharing that with IAP Paris and so on. So that was my first exposure to a bigger collaboration, not LIGO, but Virgo side. And after that, I think again I went back to doing more theoretical stuff. When I came back, of course, I think we all were at the same time. We initiated this Indian chapter of LIGO, and that's probably when I got more into this kind of thing. So that's my slow turning into more.
So you basically joined the community, although you were already contributing to these efforts.
Yes.
You joined the community when you went to Orsay for your first postdoc. Okay. And as you already mentioned, you were part of Professor Bala Iyer's pioneering group at RRI, a team that laid the theoretical groundwork for gravitational waveform modeling well before the detector saw anything, right? So how do you look back on those early years? So that's one part of my question. The other is, I've always wanted to know what has been Bala's influence on the way you think about gravitational waves and the way you think about research in general.
Yeah.
I asked this specifically because we have heard folklores about how organized Bala is, and that he could fish out a paper, once he has put it in his cabinet. Those kind of folklores. So if you can, explain.
Yeah, so I think my, kind of looking back into those ages, I think those were the times when I think we were both kind of colleagues. We write all the papers on the post-Newtonian modeling would start with saying that compact binary sources are the most promising source of gravitational waves. And at that point, no numerical relativity was there and so on. So mostly theoretical post-Newtonian type calculation was kind of driving the entire data analysis thing, because they wanted to do something to data analysis. So those were like, since then, of course, things are kind of evolved. So I'm happy that I happened to, kind of work in that kind of thing where I felt that whatever I'm doing is going to make an impact, which eventually it did. Though it was not clear at that point that when will the detection happen, but it was happy to see that whatever theoretical developments we were doing were kind of driving the field. And I was very happy to belong to that kind of time. Regarding more of the second question, of course, Bala is very strict and organized. That was strict was for my first half of my PhD thesis, because where he set the ground rules for me, what one should be, one should not be. But the second half, when he thought that, okay, maybe this guy is okay, I had a lot of liberty, because I could, we would chat for a long time about data analysis problems, because he is more of a theoretician. He was interested in data analysis aspects, right, which I was trying to pick up. And so we had very, on both topics, we used second half of my PhD, we had very interesting open conversations about these things and so on. And so what I learned from him is, of course, be systematic and learn. So one thing he kind of told me in my PhD days is that he always made me learn astrophysics, because he felt that once gravitational wave detection happens, it's going to be astronomy kind of revolution, not some theoretical thing. So he made sure that I attend all the astrophysical seminars at RRI, which was a very active group at that point of time. I had many friends in astrophysics group who helped me, who is responsible for whatever astrophysics I know now and so on. To me, it is his he had persuaded me to interact with the astrophysics group more and learn as much of astrophysics even at that time, which is now helping me a lot. And the third and maybe the most important thing he told me is that if you cannot explain your research to a school kid or a college student, I think then there's no point. So he made sure that I read many popular type books and try to articulate whatever I'm doing for communicating to kind of younger people. And I'm grateful, because I am not saying I'm the greatest communicator or something, but I feel good whenever I try to think.
So that has had a very deep impact.
Yeah, because it was clear. It was totally clear to me that that's very essential part of what you do, whatever you do, wherever you go, and so on. And probably the last and most important part was to tell me to always remain grounded. It doesn't matter what you work on.
Which I think summarizes Bala.
Yeah, I think so. To me, this is what these are the qualities I learned from that.
Fantastic. I think this is also new. Although I know you for several years, I think this is one aspect that we have never discussed before. And thanks for sharing this. So let us move a little bit to the science of the waveforms, and something that you've been doing and you've mastered over the last 2 decades or so. And tests of GR. So the post-Newtonian work that started at Raman Research, and now it basically underlies nearly every inspiral model in LIGO's analysis. So in brief, can you summarize how this has evolved since those early analytical calculations? How has this approach, how has that?
Yeah, so I think this all started with the earlier works by the French group, and it started much early on, but the concrete contributions to the LIGO events happened with the PhD thesis of Luc Blanchet, for example. And since then, both Luc Blanchet, Thibaut Damour, who was Luc's advisor, and Bala Iyer, they had a very fruitful collaboration lasting over. Even now, I think they're collaborating. So that is to me what led, because what you need for analysis is very accurate waveforms. Only when you will be, efficiency in searches will go up and your estimation of parameters will become good. So the kind of development of very accurate waveforms, starting from going order by order in the post-Newtonian theory, has happened from maybe in early 1990s to even now they are trying to improve it and so on. So to me, it was good to see this entire thing kind of unfolding in front of me, because the most accurate waveform that one had until a few years came in 2004, which is when I was a PhD student. I have seen Bala trying to finalize those papers, very long calculations, and trying to make sure every bit and piece what checks he would do and so on. Of course, those were the standards that I had to also follow, because to make sure that they're very long calculations, very complicated ones, it's important that you don't get any numbers wrong there, because it's going to be used in an analysis. So those kind of responsibility was also conveyed, and it was good to see how things kind of unfolded. And things, I think, they are still extending to 3p and 4p and so on. But yeah, that's my.
So it's also an exercise in how to organize very complicated calculation in an organized way.
Exactly. So I think there are many things you cannot miss a factor of 2, sine and so on. This extremely very sensitive calculation. So what we do is that there are multiple people who are collaborating. Each one of us will independently calculate this and cross check. Right. So if you and I compute and we don't agree, then it's a problem, because we don't know who is right. Yeah. So it's both of us will go back and try to find out who is right, or we communicate, and it's very open conversation. I mean, something I may be making some mistake because we're humans, and it is good when even Luc Blanchet, who's a very senior person, he would independently compute the same thing I did and will check with me. So there's nothing as great as.
So continuing on that same topic, so what do you think are the most urgent challenges now in the waveform modeling? Yeah. For instance, we have so many additional bells and whistles that we can model now, which was not possible at the time that you started your PhD. So could you kind of and also the reason I asked this was because now the detectors are getting more and more sensitive.
Exactly.
So I think that also
folded in. Yeah.
Yes.
Yeah. So I think, as you know, when the detector become more and more sensitive, our ability to probe signals kind of finer and finer kind of increases, right? So therefore, we need waveforms that are as accurate to that kind of sensitivity. Right. This is a challenge. That's one thing. That is means our existing binary black hole waveforms and binary neutron star waveforms and so on have to increase kind of accuracy to that kind of level. On top of it, it's a very complex dynamics. It can have precession, spins, tidal effects, and so on. But you also need a waveform that includes all this physics. So there are two kind of orthogonal challenges. One is to include more and more physics into the waveform so that they are more realistic. Second one is to increase the accuracy of the waveform so that they are, we don't run into systematic biases when we try to analyze. Both of these still are the most important kind of problem. There are effect of precision, spin-induced precision to be taken care of. Neutron star waveforms are still, there is a lot of scope for improvement in terms of how you deal with equational state of the system and so on. And of course, getting more and more, there are different regions of the parameter space, like binary black holes. Equal mass binary black holes will be having a different feature compared to unequal mass ones, and how unequal mass there can be and so on. So there are this kind of different variety of waveforms which populate different regions of the parameter space, and more physics, which makes it more and more realistic and closer to the real signal. These are like 2 or 3.
So the job is never done, right?
It's never done. I think as the detectors improve the sensitivity, we have to keep on computing more and more accurate waveforms.
The challenges become even more intricate and requires more physics to kind of.
And as you go to more and more accurate, it's very challenging to increase the sensitivity, like detectors. Yes. It's very challenging to improve the sensitivity detector. Similarly, increasing the accuracy to more and more is equally challenging. So these are like interesting two kind of thing, completely different ways.
So I also wanted to know from you, so how have the test of GR, so do you have multitude of these tests of GR? I remember your paper with Satyaprakash long time back, where you were talking about consistency between the post-Newtonian coefficients and so on. So I think that is where it started, this whole thing started. So how have these tests of GR matured from GW1509? So if you look back 10 years from now, there was a flurry of activity immediately after the discovery for various people who were developing tests of GR suddenly became active. I mean, we did not even know about some of them. And naturally, I mean, they would all want to put it to test with the new discovery. So going from the journey between GW150914 to the latest O4 catalog, how has this TGR journey been?
So I think, as you said, that what we do in the initial event is that we have a binary, we have detected a signal. We want to ask the question how consistent it is with the predictions of GR. That is what we did, a minimal kind of thing. But then once the detection was there, everybody, the community knew that there is a new tool to probe fundamental physics, right? That's what gravitational wave will give you. So people started coming up both inside the collaboration and outside the collaboration, started proposing new tests of GR, which will be testing new features which could not be tested before. So that way we kept on adding, doing more and more tests of GR, ranging from how dispersion of gravitational waves happen, what are the polarization gravitational waves, and so on. Both, so some of the ideas were inside the collaboration, some of them were from outside. We adapted them to our algorithms, and the challenge is to develop an end-to-end algorithm which is tested against simulated data, and we are sure that it gives unbiased results once you apply on a real thing, right? So with the increasing number of tests of GR, this has also become a challenge to ensure that this happens. And it is good to see that there are so many tests of GR we do now, and which are all very very different kind of tests.
So would you say that we are, in the last 10 years, we are genuinely probing new regimes rather than just making the existing tests more precise?
So, so I think we are of gravitational waves gives you very highly relativistic, dynamical and non-linear kind of regime, and in that regime itself there are various aspects of GR which we can test, and the smartness is to come up with methods which would adapt to certain aspects of GR, and if you do not find them agreeing, we have to doubt the correctness of GR. And so far, of course, we are not seeing any evidence of deviation from GR, but it's important that we put GR to this kind of test, and therefore develop more and more complementary tests which kind of probes different aspects of GR, which is itself a very complicated kind of theory.
And with the promise of better detectors and more detectors in different bands, I think the game becomes even more interesting.
Exactly. So we can do a even wider array of tests, which kind of and more sensitive test. So there again, it is important to say that if you want to do a test of GR, you need your accurate waveform again, because you're talking about deviations at a very minute level. If your waveforms do not control that kind of a minute thing, you cannot do test of GR. So again, everything will rely on the waveform modeling accuracy. It's a cycle, right? So it's interesting times, I think.
Very nice. Thanks for those insights, Arun. So let me change the gears a little bit. Let's go into India's role in this whole thing and the LIGO-India project. So you are now the co-chair of the LIGO-India Science Collaboration. So where do you things stand at present, technically and also scientifically? And could you also explain for our viewers what your role involves at a strategic level?
Correct. So I think, as you know, maybe you have Sanjit would have told in yesterday's interview also, LIGO-India is a very kind of ambitious Indian project where we are actually working actively, and we are hoping that we will get a detector comparable to the LIGO sensitivity by 2030. And scientific benefits are of course kind of well known. But what is important, as you mentioned, is to have a community to contribute to and make use of the data that it generates. So it's important to develop a community who is trained to use and trained to use this as a tool to solve open problems in astronomy and fundamental physics, right? And that's where the community role comes into picture, and that is where the LIGO-India scientific collaboration, which I'm like a co-chair, the role will be to, on the one hand, make sure that we interface with the community, broader community, encouraging them or training them to use the gravitational wave data, especially when LIGO-India data will be available. Second thing is to ensure that as data analysis component, people who contribute to the LIGO data analysis, we should ensure that our contributions are like the highest level in terms of the thing, because that's like a training. People will be applying those kind of state-of-the-art techniques to even the LIGO in the LIGO-India era, and same time learn, maybe contribute whatever we can to the kind of LIGO-India instrumentation thing as well. So the overall thing would be to manage this in a healthy way, and make sure that this does serve the purpose and generate whatever are the synergies between different communities in India, and kind of ensure do whatever is possible to make sure that the synergies exist.
Now, I think since you mentioned developing a community, I think that also neatly ties in with what you earlier said about during the and after the discovery. There were a lot of people outside the collaboration who also were tremendously excited by this development and developed a lot of tests of general relativity. I think something similar is happening in India, don't you think? Where we have a very well-trained community of general relativists, and now that this discoveries have, I mean, with the 04, I think we have more than 290 events or something like that. So I think that has generated a lot of interest in developing new tests, and kind of reeling in or pulling in these kind of people within the the gravitational wave community.
So I think we already saw in the conference that in the classical gravity communities, so they are so full of new ideas and so on, which can be all tested. And another thing, as you mentioned, like communities such as high energy physics community, like dark matter people. So there may be direct. I mean, we should use all means to use gravitational wave as a probe of whatever physics we know. Right? It could be dark matter, it could be astronomy, it could be fundamental physics. So there's a lot of non-gravitational wave to begin with people around who are excited, as you rightly said, and they're coming with ideas. And it's our duty to kind of interface with them, collaborate with them, and try to do. I mean, this is what excites us, right? To use a newly found tool to probe and answer some of the fundamental questions in physics.
Right. And I think it serves the purpose of spending public money on such a expensive instrument. But it's hard, it's very good to notice that people from across the communities are coming in to kind of
interfacing and coming with new ideas and asking us how we can collaborate
advantage of such an instrument. Okay, so let me ask you also, how well do you think you have answered it to some extent, but nevertheless, I'm just going to put it out. So how well do you think that the Indian scientific community are integrated into the broader LVK ecosystem? And do you think that we are, quote unquote, equal scientific partners?
Yeah, I think so. As you would remember, Anand, that when you and I were starting our faculty kind of career, we were a very few people. Since then, of course, we have grown in the faculty strength as well as our students and postdocs. So you can see that if you go with the, I was taking this discovery photograph we took at IUCA. I was looking at who are there, like 30, 35 people who are there, of which most of them have gone on to become faculty, this 10 years time elsewhere, which shows that, the kind of training we have given to them, some of them have come back, some of them are abroad. So I agree with you that it is important contributor, and we have done well. I would say that our kind of the contribution has significantly gone up since our early days, and we are now. Now we are contributing to every analysis that we can, or every subgroup of the LSC. We do have a representative who is really leading that one, and maybe leading some of the papers and so on. So I would think that we are
very heartening, isn't it?
Absolutely, because it's a lot to do with the. It's not about individual mentors training them. It's about the community which has helped them grow, right? And even undergraduate students who have gone on to done a MSc project with you maybe and gone on to do somewhere else. I hear very good things about from abroad also, which means that our undergraduate training at that level is also so good that there's something to be happy about.
Shine at any place.
We should be, again, as I said, we should be grounded. We should continue to do what we do. But there is all the reason for us to be kind of happy.
Fantastic. So now, if you can put on your LISC co-chair hat, I'm going to ask you a question on that. So one challenge often mentioned in large Indian projects is sustaining the interest across institutions, because it involves many institutions. So has LISC been able to build a cohesive national research culture? And I think the answer is yes, because
Yes.
you
So I think
mentioned
this is
students,
because,
but is there
we
any
have-
other aspect to it?
Yeah, no, I think even the first level of thing is that, so fortunately, as you know, that many of us who came back at the time were like peers when we were PhD students, and we have a personal rapport
Right.
at that point of time. So it really helped to gel together to begin with, right? Then we have our students, and our students are, we work with each others, going there, and with institutes also. I think we have been fortunate enough that all the institutes to which we have joined have given us kind of enough support, and and our personal rapport. So this is a combination of both institutional support to the individuals as well as the rapport between the individuals, which has helped us to grow this extent, not only on our own personal thing, but also our students and postdocs, and somebody going and visiting for a long time and kind of training them, and talking happily about each other's things. So it's something which I hope we can maintain it with our new generation of students who are going to come back. I hope it remains.
Absolutely. So I have one more question on this topic, and that is related to experimental side. So I remember that when these efforts started in about 2009 or 10, there were very few experimentalists whom, of course, with our limited experience, we could identify. So do you think we have been bold enough in investing in the experimental side, for instance, developing personnel in optics or control systems, data infrastructure? Or do you think our primary strength is theoretical physics?
No, I think it is true that when we started, our primary thing was theoretical science and data analysis. I think it's unfair to be, because if you think there are two streams of RRI and IUCA in the two hubs, and IUCA has trained like people like you and Sanjit who are more data analysis and experts in data analysis, and maybe the RRI school has been more theoretical, but they have gelled well. And now just kind of coming back to your question, you're asking about instrumental science. So when we started, probably we did not have, it was a bit of a bold thing to begin with, but we knew that the kind of, finally we need experimenters, and many of the techniques are available, like vacuum, right? Vacuum is an important part of LIGO. We know people in IPR and so on who are experts there. It's a matter of conveying, getting them on board. And optics, we know there are enough, there are good groups like RRCAT who is now leading it. So I think the kind of vision Bala and others had was the confidence to convince these existing groups that why they should join this exciting project.
So if the challenge is big enough, then you would find many groups
joining
who are scattered to begin with. They would gravitate towards that project.
Something interesting science, because we are all scientists at the end of the day.
Right.
And anything that is challenging is what
and that has happened in your opinion.
In my opinion, that has happened. I think there is still, because we still need to grow. That is true, but definitely it has crossed the kind of first barrier has been crossed. But one shouldn't take it lightly. But we should still continue to grow. We should train our, there are enough engineers and experimentally oriented students. We should continue to train them, because that's important. It's not a done deal. I'm not saying, because still we have to make a detector. But we have made the right steps, and we should try to build on what the kind of progress we have made.
Very nice. So, do you worry that this project has a very long time? So, as a LISC co-chair, do you worry that this long timeline may lead to loss of momentum and or loss of trained manpower? Because we are only if you look at, say, the LIGO project, the fruits came after almost 40 years of very long sustained efforts. So that's not going to be the story with LIGO-India, because a lot of these initial hiccups have already been ironed out, and we can take advantage of those. So what are your thoughts on retaining and mentoring the next generation through this long phase of?
Yes, so I think in terms of first question, I think as long as there are challenging questions to address. So now, the question is that you're working on LIGO-India, and what might motivate you is that what is beyond LIGO-India, right? So there are next generation detectors being considered, and the technology is more difficult. So what pushes us to do is what next. So as long as that kind of extension is there, I think we can maintain gain the momentum, hopefully.
Right.
And now, in terms of training, I agree with you that it is all about how much we generate. I mean, like we have successfully generated a data analysis community now, starting from almost like a few people. Similarly, I'm hoping that we can generate a lot of instrumentation expertise, which could go on to not just beyond LIGO-India. And LIGO-India is like one milestone.
Yes.
And there may be future missions which may be in gravitational waves, which could be. Then we have we start with a much more larger pool of instrumentation people who could contribute. So I guess that the kind of opportunities that exist now should kind of make them, should be driving them.
Yeah.
That's my hope. But that time we should be conscious and we should be.
That's a fantastic message, I think, for
younger people.
Yeah, exactly.
Yeah, because it's not. Do not think that LIGO-India in the next 5 years that's done, right? There's a lot of things to be done. It's only a
beginning
point. It's the beginning of a new era.
Absolutely.
And with different bands, and India is playing a very leadership role in every aspect of the science in the thing. So there is. I mean, if you enter into the thing, you are guaranteed to have many opportunities which are like unexpected when you entered.
Right.
So I'm hoping that will drive both the kind of younger folks who are entering as well as those who are really contributing now to keep up the momentum.
Fantastic. So I now would like to change gears to the last leg of our interview. So are there any particular science goals that you're most excited about in the future? I mean, if you can mention a few and then tell us also why you are so excited.
Yeah, so I think if I, of course, there are like 5-year, 10-year, 15-year and so on. Like next 5 years, of course, because it's going to be LIGO and LIGO-India joining and so on. So, so we are yet to discover a wide variety of sources, which are, we are still detecting various classes of binary black holes. So one thing which we are not seeing is a neutron star black hole merger. That's a mixed kind of a thing, which is accompanied by electromagnetic emission. So like a GRB, we had one binary neutron star like that, but we do not know whether neutron star black hole mergers can give you light at the same time. That is something which I would like to see as a multi-messenger neutron star black hole observation. I don't know when that will happen. If it happens, it's good, but if you see a bunch of neutron star black holes without a multi-messenger counterpart, electromagnetic counterpart, that may be telling us something about that source itself. So that's one thing. On the more of an astrophysical side, again, I'm hoping that we detect black holes. We need to now understand how these black holes are formed. Based on whatever we have, whatever mass and spin we measure, we need to come up with schemes which will tell us how they were formed. And that is an astrophysical kind of scheme of things. And I'm hoping that we can develop schemes which will tell you where these black holes came from. And so on. I can keep on going about specific examples. These are two things which I think would excite me the most. Multi-messenger neutron star black hole observation and understanding the formation channels of compact binaries.
And you think that when LIGO-India joins the mission, when we attain the first lock, some of these questions could be answered?
Exactly, because with LIGO-India will help, and especially when in locating an electromagnetic counterpart, we know that LIGO-India's localization capability in a global network is so unique that we will have a very unique role to play. So I'm hoping the first detection doesn't have to wait that long, 5 years, but even then, so it's not the first detection, it's about a population that we detect. And to that, I think definitely LIGO-India and its source localization capability will have a huge role to play, and we should be looking forward to those kind of exciting times.
So what would you tell a young physics student in India who dreams of contributing to gravitational wave astronomy?
Yeah, first thing I would say is that these are excellent times, and not only for LIGO, there are nanohertz observations which are happening with pulsar timing array, and now so this is the right time to get into this field and understand what are your aptitudes and which are the kind of areas which you can contribute. Fortunately, he or she will have opportunity, there will be some nearby institute which he or she can go and talk to and understand what are the kind of things happening. We are not that narrow anymore, we are now much more spread out, and maybe do a summer internship to assess their own aptitudes, and then try to see which of these areas they want to contribute, and then join a PhD program and then try to contribute. And I'm sure that once they get into the thing, our community will make sure that they are happy enough
and now we also have very periodic LIGO-India workshops.
Exactly.
So I think that is also one more area where I think
exactly we have LIGO-India workshops, training workshops to which they can go and understand what are the kind of challenges in different fields, both data analysis, instrumentation, and so on. Definitely it will, because it's important that when we cannot there there are different aptitudes of people, and they should do things which excite them. And I think going to this kind of the interactions of different levels will help them assess for themselves what kind of things excite them, and make solid contributions towards these activities.
So we'll end with one last question. So what keeps you motivated? I mean, again, looking at the LIGO-India scientific collaboration. So what keeps you motivated in steering this enormous collaborative experiment?
Yeah,
I mean, from your own personal point of view.
Yeah, I think what drives me is to see that the students and postdocs we have, not me, I'm saying community have, they're going to do very well and contribute at the playing a leadership role is already, and it's like it's so heartening that it is good enough for me to drive. Not as not any even as a member of the collaboration, I'm happy to contribute just to see how our students, not just mine, as I said, contributes at the highest level, and we should improve, still keep on improving, and make sure that our students and postdocs are trained and they to do the highest quality of research. This is what to me kind of drives, not just anything that is personal to me.
Fantastic. Thanks a lot, Arun, for spending time with us and for sharing your insights.
Thank you so much. It's great
topics. We covered a lot of topics, and I'm really happy. I hope it's useful for our viewers as well.
Thank you so much.
Thank you very much.
Thank you for joining us. Another remarkable guest is coming up in our next episode, so stay tuned and do share your comments and suggestions. I'd love to know what you think and what you'd like to see next.